extremely pleased. Yeah, okay, great. So today we're extremely pleased to have Bill Halperin of Northwestern University to give us the talk. Bill is very well known to the community, and he had done tremendous amount of work both on helium and also on low temperature physics of the UPT3 and various other materials. And he also done quite a bit on iron pegmatite, for which I have collaborated with him for quite a few years. Although we haven't done too much as he has. But anyhow, so Bill is the winner of London Prize 2017. So today he's going to tell us about the microscopic quantum states in triplet superconductors. And this is the second part of the series that we had from last week when Jim Saul gave a very nice talk on the theoretical aspect. So today I wanted to have a Bill to give a sort of a foundation of experimental aspect of the sort of we call the story of UPT3. Yeah, it's all yours, Bill. Thank you. Thank you again.
Thank you, Pencheng. I'm going to emphasize a little bit of this sub-heading here, anisotropic impurities, which can figure importantly in all of our quantum materials at some level, except for pure helium-3, which, as most of you know, when at low temperatures in the superfluid phases of helium-3, which is a triplet superconductor, there are no impurities except the boundaries. So consequently, I will make a contrast and a comparison between anisotropic impurities introduced in helium-3 into the pure state, plus a comparison with that in uranium platinum-3 as an example of a putative triplet superconductor. And I want to acknowledge explicitly in the helium-3 work that I've done, as well as uranium platinum-3, Jim Sauls as a collaborator here at Northwestern University, Morton Eskildsen at Notre Dame for work we've done together on uranium platinum-3, Anton Vorontsov in both cases, and David Seidman, who was very instrumental in helping me and working with me to set up a crystal growth facility where we've made some good crystals of uranium platinum-3. And Dale Van Harlingen and Aaron Kapeltunik in their work on uranium platinum-3 crystals that we've grown in that facility, as well as Jan Kitje, former student, and Pencheng Tai, who just mentioned some of the collaborations we have together. Others, including Eric Bauer at Los Alamos, John Saunders at Royal Holloway, Jivak Parpi at Cornell, and Norbert Mulders, unfortunately, who has passed away in the latter two cases on helium-3. So with that, no further ado, as you know, there is an interesting comparison between helium-3 and uranium platinum-3. I say in a joking manner that it's unusual that we have a comparison between the lightest and the heaviest of various compounds, elements in one case, which is summarized here, multiple phases. There are multiple phases, and that has a commonality in their quantum mechanical behavior. The helium-3 was discovered in 1972, now almost 50 years ago. And, and uranium platinum-3 in 1984 at Los Alamos, Greg Stewart and colleagues. The work that has followed on uranium platinum-3 has not been exactly in a parallel, but what we've discovered is that the multiple phases of helium-3 and the multiple phases of uranium platinum-3 have some commonality. And as you will learn a little bit later, if you don't already know, it's the A phase of helium-3, which is chiral superfluid, and Jim Sauls pointed this out in several specific examples of experiments and direct experiments of the chiral symmetry. And in the case of helium-3, it's the so-called B phase, which is the chiral phase, at least according to one of the leading theories. And this goes back now in low temperature physics 100 plus years ago. I wrote a perspective on this for Nature, covering superconductivity in helium-3 a few years ago. And now in the present day, here's my lab, and you can see there's a little bit more gender diversity. And I'd like to now move to what we can do. And that's built on a technology that followed with the invention of the dilution refrigerator, manifest here in a dilution refrigerator, which is a so-called dry fridge at National Laboratory of the Fermi Lab in the SQM SDOE collaboration, Alex Romanenko here. And then here at Northwestern, not so far away, actually, is the bottom end of demagnetization cooling setup with a silver cell in which helium-3 sits to cool down various samples and NMR coils. And we've got a stack of NMR coils. This is for thermometry and the other 3 for samples. And we can simultaneously take data on different kinds of samples. And in that work, we're using demagnetization cooling. That means that you pre-cool and reach an entropy at some dilution refrigerator temperature. You decrease the magnetic field. And when you go down to relatively low magnetic field, you can achieve temperatures as low as about 100 microkelvin. Not in my laboratory. We're not quite to 100 microkelvin in my laboratory, but one thing we do specialize in is very low heat leaks that allows us to hold millikelvin temperatures and below for 1 month at a time for one demagnetization, which means a lot of data. Now back to the phase diagram. It's pressure versus temperature, 2 phases, and then the normal state on the right-hand side here. The book by Volhard and Vifli is really our foundational book of summarizing the details of helium-3. I strongly advocate that book. This is the situation in zero field, and I'll mainly talk about zero field properties. And what I would like to outline for you is how do we know what the microscopic state is of these A and these B phases? Keep in mind, okay, so the temperature scale here is around 1 millikelvin, and we can proceed to rather much lower temperatures than that. Now back to this commonality of the multiple phases. And the point I want to make is that for unconventional superconductors, which these both are, I think there's no question about that, that is, they break symmetries of the normal state beyond gauge symmetry. They're sensitive to both potential and magnetic scattering of impurities. And sometimes we learn a lot about the nature of the microscopic states of superconductors when we put impurities in, and that's going to be part of the thesis today. So if you have a vector order parameter, there can be, and often are, multiple nearly degenerate phases, and the differences between those phases comes in part from their independent sensitivity to impurity scattering. And not only am I going to talk about impurity scattering, I want to emphasize anisotropic impurity scattering. You'll see why, I hope, soon. Now we know that the A phase is up here is a chiral axial state, a P wave state, and the B phase is a non-chiral isotropic state, also in the P wave manifold. But what I want to tell you as a lead-in is how we get that information. How do we confirm that that's the case? It's kind of the paradigm of how you identify complex or complicated, if you wish, unconventional superconducting states. And so I start here with the susceptibility, which for a superconductor, this would be the night shift. In the case of helium-3, it's not electrons, it's nuclei. And from the normal Fermi liquid, the susceptibility can be determined directly from the nuclear magnetic resonance intensity. And you can see there's no change to high accuracy when you pass into the so-called A phase at adequately high pressure. In this case, around 30 bar. Now, interestingly, at that pressure, there's an equilibrium there's an equilibrium range of temperature for which the A phase exists. However, even in zero field, there will be a non-zero A phase at high pressure. And most importantly is the B phase susceptibility, which involves the zero spin state of the multiplet, the triplet of the spin state of the superfluid in this case. You can see that traces, see the dashed line, it traces up, and it was observed by John Wheatley, I suppose, first that this trace intersects here at exactly the same temperature that superfluidity is discovered in the A phase. And therefore, these A and B phases must be of the same, in the same multiplet of degenerate states, except that the degeneracy is removed if from the A phase compared to the B phase by strong coupling. That means since the susceptibility is the same as the normal state, that we have an equal spin pairing state, and that triplet state is specified by the spin quantum number being 1, and therefore it being odd parity. There's no, well, there's negligible spin orbit interaction. So these are good quantum numbers, and we're looking now which is the odd parity partner here to make the A phase. And correspondingly, what is the nature of the B phase? Because there are a number of states in this manifold, which you will see in a minute. And the way it works is this, best seen from the heat capacity. And here I show the measurements of Dennis Graywall back in 1986. And you can see on cooling that the specific heat has this classic jump in the heat capacity. It's almost a factor of 2 of the normal state value at high pressure. And then it decreases, and you can see it's exponentially decreasing at low temperatures, and that is a clear demonstration of the isotropic energy gap, which I've sketched down here at the bottom. However, in order to choose which of the possible B phases might be the B phase, let's go to the theoretical side, where Balian and Wertheimer actually predicted that this B phase that it turns out we are observing is the isotropic state, known now as the Balian-Wertheimer state. This was done in 1963. But Verdovin, at about the same time, not only did he take that same state, but he looked at the order parameter collective modes, and he found that, interestingly, that in the energy gap of a quasi-particle pair, that's 2 delta, that there are sub-gap states, well-defined, at square root of 12/5 and square root of 8/5 of delta. And here, I've just taken a copy from the original manuscript here by Verdovin, and you can actually see he wrote 8/5 and 12/5 here for these sub-gap states. And it turns out these sub-gap states have been organized in the theory. They are, in fact, total angular momentum 2 states, J equals 2, and the minus and plus refer to the order parameter components, which are responsible for forming the structure of the subgap state. These being the imaginary parts of the 18 component order parameter for helium-3, and these are the real parts down here, mainly the spin degrees of freedom sensitive to the square root of 8/5. All right, so I bring this up for because at 0 temperature, you have non-zero collective mode frequencies. These are bosonic Higgs modes. And as a function of temperature, I show you here that they heal to 0 energy or 0 frequency if you're measuring with acoustics, as you might expect at TC for a second order transition. But interestingly also is that these states split in a magnetic field. So if the field is non-zero, there should be, given J equals 2, there should be 5 states for each of these. And in fact, this has been observed experimentally by acoustics. I want to tell you a little bit more about that, not the whole story, but the most important aspect is that these microscopic states are a characteristic of the B phase, which has an order parameter that is defined in spin space as being proportional to a rotation matrix between orbital and spin space. And that rotation matrix is the manifestation of spontaneously broken relative spin orbit symmetry. It's not the dipole interaction. It is an intrinsic, spontaneously broken symmetry, which is the classic symmetry. It is the characteristic symmetry, I should say, for the B phase in the BW state. So if we can observe some aspect of that, you have a direct measurement of this being the so-called Balian-Wertheimer state. And here it is. What was observed here at Northwestern, first theoretically by Moores and Sauls, now some years ago, that transverse sound would propagate in superfluid helium-3. This goes back to Landau's prediction that even in the normal fluid, there should be transverse sound. Both of these statements should be of some surprise to you, because liquids, and especially superfluids for the latter case, cannot support shear, so there can't be transverse sound. But in fact, the predictions are based on the excitations in the of the normal Fermi liquid in this case, and here for the superfluid. And without much more ado, we discovered this transverse sound as predicted by Moores and Sauls. And here in the sketch that John Davis prepared, you can see the oscillations associated with transverse sound, the polarization being perpendicular to the propagation direction, which I'm moving my cursor in the direction of. And to do this kind of experiment, you need to have an acoustic cavity, and you measure the Q of the cavity basically, and that as you change the velocity of this transverse sound, you can see resonances here. And the way this comes about, I should add, from the theory, is an off-resonant coupling between one of those subgap states, the square root of 12/5 state, and the density which allows this transverse sound to exist in the shaded region, which I'm plotting again as frequency as a function of temperature. But you might say, well, this transverse sound, which is a direct manifestation of the coupling between orbit and spin, has modulations in it. And those modulations correspond to the Faraday effect. Everybody knows the Faraday effect of light, which is a transverse wave. But similarly, if you apply a magnetic field along the direction of propagation, this is what you get. This is at 100, at 0.1 Tesla. And in fact, you can observe rotations of the transverse polarization in a 30 micron cavity up to 1,700 degrees. It's truly fantastic. This experiment was first launched by my former student, Yoon-Suk Lee, now at the University of Florida. All right, now the order parameter in the B phase features the unique broken relative spin orbit rotation symmetry, and in a triplet state, therefore, defines it to be an S equals 1, L equals 1 state. So that's a pretty firm identification. That's kind of the smoking gun type identification that you like to see. But the A phase, let's talk about the A phase. I know it's an equal spin pairing state, but there could be a bunch of those. Now, the way that is going to be done is, first of all, as you have seen from NMR, that you measure the frequency, the susceptibility, and the susceptibility is in an NMR spectrum is the integrated area under the spectrum. And the A phase has, in these data, these are actually data, not sketches. You can see they're the same in the normal state and the superfluid state, and rather much less is the B phase susceptibility, again, as I had pointed out earlier. However, the frequency of the shift that's observed here, that shift is due to Leggett back to 1972, is proportional to the average energy gap squared. And I show you data from Doug Osheroff's group with Peter Schaeffer shown here with great accuracy. And this behavior, if you look at it very carefully, you can see that there have to be nodes in this gap. It's not an exponential behavior. So it's an equal spin pairing state. And we know of a number of states in the manifold. The axial state is the one which we know is true, which I've just talked about. There's the polar state, which was recently observed by our colleagues in Moscow by Dmitriev's group, and in collaboration with the Aalto University researchers found have found half quantum vortex in this state. And then say the planar state. Now these latter two are time reversal symmetric, and the axial state has broken time reversal symmetry. But both chirality and broken time reversal symmetry can be determined experimentally from this beautiful experiment at RCQM by Ikegame and colleagues, including Kimitoshi Kono, published here in the Science magazine, involving electron bubbles. Now I want you to think of the electron bubbles below the surface of a free surface of helium-3 being driven to the right by an electric field, and those bubbles are impurities. You think of them as impurities, which will have then a mobility that skews to the right or to the left, potentially, because the angular momentum is normal to that surface by condensation energy, and it points either up or it points down. And therefore, there will be a skew to the right or to the left that is a direct manifestation of the time reversals, the broken symmetry of the angular momentum up here. And that was shown in this work. And the agreement with the theory of Sols and, and Shetsov is remarkable. That was discussed at some length by Jim Sols last week. And so in summary, as I've said in words, the B phase is the Valium-Wertheimer isotropic state, and the spin part of the state is shown here at the right. The orbital part is simple, it's just it's a scalar. And similarly for the A phase, we have this classic P wave character to the order parameter, and it's an equal spin pairing state. Now, this brings me to impurities. Let's stick some impurities in here. There's a summary of how what happens when you put impurities into aerogel or superfluid helium-3 into aerogel. That's the aerogel is the impurity, not the helium-3. In Physics Today article that Jivek Parpia and Jim Sols authored with myself, and then a review here in the Annual Reviews in Condensed Matter Physics. So here's the aerogel. So the key question for the neophyte is, well, why would you ever think you're going to put helium-3 in there and get anything sensible? Well, you'll be surprised. I mean, if you don't know that the transitions to superfluidity of helium-3 in this environment are very sharp. The phases are extremely well defined. And although this distance measure is 200 nanometers, that's on the scale of the mean free path. The mean free path is actually larger than that. So that's approximately the scale of the size of this image that I'm showing you. And this is a SEM picture, which was taken by undergrads, most recently since Yasai. So what kind of phase is this? So this is a new kind of problem, the problem of impurities in a well-known superfluid. And here you can see the frequency shifts that I'd mentioned previously, onsetting, indicating the onset. This was done also slightly before by my colleagues at Cornell and Jivek Parpia's group measuring the superfluid density. And I remind you that the frequency shift here is proportional to the square, or the average square of the energy gap. And now, we know it's a superfluid. And so if you follow this line experimentally, the first thing that happens is you note that the transition to the superfluid is reduced from that of the pure state. And then you wonder, well, what kind of phase is it? And just to make the point that these are transitions from the normal state to the superfluid state, which are very sharply defined at the level of a few tenths of a %. Up here, I'm saying that the transitions are extremely narrow, very sharp. And the susceptibility is the same in one of the phases. So obviously you're going to conclude that that one would be the A phase, and the B phase is a susceptibility, which, okay, you're going to call that the B phase, probably. But what you don't know is that in zero field, there isn't any A phase. It is gone. And that can be done through measurements, acoustic measurements in this case by Guillaume Gervais in my group. You're doing acoustics, and you can determine in zero field, or effectively zero field, that the entire phase diagram is B. Similar work by NMR using a measurement in a magnetic field, but extrapolating to zero field has been done in my group using NMR susceptibility tools. And the interesting point, I think the most interesting point, is that theoretically in Jim Sols's group, in collaboration with Eric Thunberg, that they showed that the states that will be favored are isotropic states if the scattering of the helium-3 quasiparticles is isotropic. So isotropic scattering favors isotropic states. So why not make the anisotropic and really check on this? So that's what we did. Here's the numerical simulation of an aerogel. So you can see there's local anisotropy, but the mean free path is much larger than this. So it averages over all these little local details. And what you want really is global anisotropy. And so you can achieve global anisotropy by taking one of those aerogel 5 millimeter diameter, 5 millimeters long sample, and you just compress it to make it anisotropic, or you stretch it to make it anisotropic globally. And that's key, because then the transitions are preserved in their considerable sharpness. Oh, and what do you find? Well, if you, in the strained aerogel by 14%, the entire phase diagram goes from B, from B to A. It becomes chiral. So you can tune the chirality of the superfluid state by introducing anisotropic scattering. That's really a great observation, and that's not all. It's the A phase here. I'm not showing you the great deal. Obviously, we're not doing electron bubbles in this material, but nonetheless, we can, from frequency shifts in NMR measurements, determine that this is in fact the A phase. And over here is another phase separated by these white squares. So what's this phase down here? Well, Jim Sauls predicts that should be biaxial state. And I think we've shown, and we're still discussing this matter, but I think we've shown that this is the A phase as well, but it's a different texture. The orbital angular momentum flops by 90 degrees along this line. Very interesting. It's particularly interesting if you want to control the quantum mechanical order and do experiments which are sensitive to the direction of the angular momentum. So in summary, isotropic isotropic and anisotropic aerogels have been quite interesting in exploring and engineering how the phases are favored one way or the other in the presence of impurities, which are obtained by quenched disorder. I want to turn to uranium platinum 3. So some of what I've told you, I believe is replicated here in uranium platinum 3. And here's the phase diagram again, both in blue for magnetic field along the z-axis and otherwise perpendicular to the z-axis, as I've shown in red. And you'll note that the blue curves for fields along the z-axis show evidence of polylimiting. That is an important part. Now, what is the origin of these different phases if they're all from the same multiplet, if they all belong to the same multiplet of condensed states? And so what's invoked is that, let's say at zero field, there is a stable A phase region, which is caused by a symmetry breaking field. And soon after the discovery of this phase diagram, it was shown by Epley and colleagues that antiferromagnetism existed at around 6 degrees Kelvin, much higher than this half a degree Kelvin range. But it was extremely small moment antiferromagnetism, about 1/100th of a mu Bohr. And here was the neutron scattering result for the directions of the order of the spin order of the magnetic state. However, this scattering experiment was done without the same resolution that Pencheng Dai is capable of doing. And more recently, he's shown that, in fact, there is no static antiferromagnetic order here. So that can't be a static symmetry breaking field. Now, here in my group, after we set up this crystal growth facility some years ago, we were able to grow pretty good crystals. Here's a crystal we call ZR8. It has a very high triple R, but not the best. The best that we've gotten is 1500 from ZR8. It's around 600 or 700. ZR11, another one is around 900. So we get around 1000 triple R and very narrow transitions, or like 1.3 millikelvin. I'm going to come back to what I mean by this triple R and what its relevance is to understanding the superconducting states. And the approach I'm going to take here is different from helium-3, is that I'm going to follow the proposal by Jim Sauls, published in Advances in Physics, for a two-dimensional representation, the 2U representation, which is a F wave state, and for which the order parameter has this structure. And for this particular state, I'm going to then ask, is experiment consistent with that state, rather than discuss all the other possible states that have been proposed. And in particular, what one finds for the B phase is that the Chern number is 2 for this state, and hence, if you rotate around the Fermi surface, you get a phase winding of 2. And Dale van Harlingen, with crystals that we supplied, I think the triple R was 950 for this, he was able to do phase-sensitive interference experiments. This is a pseudo Fraunhofer pattern, which you've seen in the context of cuprates from Dale's work on that topic. And Joel Strand and Dale van Harlingen showed that, in fact, you get a symmetric pattern here about 0 applied field, whereas what you would expect theoretically for other states, again, of the 2D representation is E1G and E1U states. You can see an asymmetric dotted blue distribution for magnetic fields as compared to the E2U states. So this really, from a phase-sensitive experiment, suggests strongly that you have E2U. And also, Joel Strand and Dale van Harlingen did these very nice directional tunneling experiments. You can see our crystal here is black, but they've affixed electrodes around the periphery. And here, another crystal with much more closely spaced electrodes prepared by Fib. And then they measured the onset of the critical current. And you can see that as a function of angle, that angle specifying the electrodes, each dot here in this plot is an electrode. And then you can see that there's a clear onset at 45 degrees, 45 degrees from the A axis. And this is done in the A phase, in that at very low field, the equilibrium window of the A phase. And from the theory, the E2U theory, you expect longitudinal nodes here cutting through the equatorial plane, such that at an angle of 45 degrees relative to the A axis, you would expect to see nodes. And this is the node right here. However, it's not so simple, because there are potentially 3 domains which form. And these domains, that is, you have a hexagonal crystal, and the A direction and the B directions will be 3-fold multiplets. And so, in fact, for the E2U state, which I've just shown you, it's not just at 45 degrees, but you'd also expect a node at 15 degrees and at 75 degrees, or you would expect at least macroscopically to get a distribution of nodes with these 3 orientations, whereas there is nothing at 45 degrees for E1G or E1U. But that's, excuse me, but that's not the case. There's only one node that's observed in the Strand van Harlingen experiment, and that proves that you only have a single domain. So that is very interesting on fairly significantly sized samples of the superconductor, that they're single order parameter domain. Now the second class of experiments here from the polar Kerr effect is also very beautiful in that the onset of Kerr rotation takes place in this shaded region that I'm showing you at a temperature which marks the onset of the B phase and not the A phase. The A phase is, of course, the normal to superconducting phase right here on the right. And so the onset of Kerr rotation at this point pretty clearly indicates that that's characteristic of the B phase, and which you might expect such a rotation from broken time reversal symmetry. And the reflection in the Kerr effect is from a C-axis facet. Actually, this is a facet cut out of a crystal. I mean, this is an as-grown surface, and it's very nice for the experiment here to have a pristine C-axis facet. Now, I come to the collaboration I've had in recent times with Morten Eskildsen at Notre Dame, where we have performed small angle neutron scattering from the vortices, and particularly in the B phase. Now these vortices, normally you would expect to form a lattice, at least ideally. And the sketch here of the lattice of vortices, the red portions are the highest field portions, and the blue here are the lowest magnetic field, local magnetic field from the circulating currents in the vicinity of the vortex. And that field distribution is plotted here. This is from Vesna Mitrovic's paper in Nature. And so what does, what did we do most recently? First, this was started by Bill Gannon and other colleagues from my group, and also similarly students and in Morten Eskildsen's group. But here I'm showing you specifically more recent data from 2020 that we've published, where Keenan Avers was the first author. Now, what you see here on the top left panel is you see 3 diffraction spots from the small angle neutron scattering, which comes from this vortex lattice. There are another 3 below this line, which we don't spend any time trying to integrate to obtain because of, time is money, basically. So we concentrate up here, and you can see that there's therefore a 6-fold pattern, which you would expect for a triangular lattice. However, this is at low field. This field is approximately the same field that Huxley did small angle neutron scattering with. But if you carry to larger magnetic fields than what Huxley had performed, you can see that this fellow up here starts to split apart. This is in 0.4 Tesla, now up to 1 Tesla. You see it splits apart more. And then at even higher field, it seems to decrease in its splitting. So these 2 diffraction spots are characteristic of 2 domains, 2 vortex domains, which we discussed the origin of in this paper here that I've quoted in 2020. But it's sort of interesting that this develops as a function of magnetic field. And the reason it develops as a function of magnetic field, we ascribe to distortion of the energy gap, field distortion of the energy gap, well known, we should add, in helium-3. But the decrease with further decrease, further increase in magnetic field shown here, that seemed to be a bit of a quandary. And so let me tell you about how we explored that. And that's in this phase diagram of magnetic field and temperature, a proposal which actually appears in Taki Tokuyasu and Jim Salz's paper back in 1990. But our paper on small angle neutron scattering had to wait 30 years, apparently. Nonetheless, the idea was the following. So you cool your sample down in this phase diagram. So you follow this temperature axis here, then you come up this way. You come up this way and you go into the normal state. Then you decrease the field into the C axis, the C phase of uranium platinum 3, which is a non-chiral phase according to E2U. And then when you pass into the B phase, the chiral phase, the magnetic field that you have imposed and which is present when you pass through that phase boundary orients the chiral axis. And then you stop at this blue circle, and then the magnetic field and the chiral axis are well established. We call this plus plus. But that's not all. According to the suggestions in these calculations that have been made by Tokuyasu and Salz, why don't you just decrease the magnetic field? The C-axis, the chiral axis is fixed. it can't change. It costs condensation energy to switch the chiral axis, so that's going to stay fixed. But you cross through the Meissner phase and back on to a negative magnetic field of the same value that you had previously when you took your data there, and you compare the vortex lattice that you got and the diffraction pattern here in this bottom blue circle, and for good measure, you repeat that on the just reversing the order of negative and positive magnetic field. So that's the plan. And here are the results. The results are that I can summarize on the left if you wish. For this diffraction pattern, you can see that the minus 1.1 Tesla experiment has a smaller splitting, not a lot smaller, but measurably smaller than the plus 1.1 Tesla. And that can be done as a function of field. And you can see then that this onset of irreversibility, if you wish, for plus versus plus minus experiments, or minus plus versus minus experiments, start to deviate in the frequency, the angle of the splitting when you go to fields which are of the order of 1 Tesla and beyond. And this was carried out to just slightly above the B to C phase transition. So reaching these high fields requires rather pure and clean systems to make the background suitably tolerable. As I say, this seemingly unusual result was just recently published. Now, let's keep in mind the order of events here. I mean, the size scales. Okay, let's go back if you wish. So I'm at a fairly large magnetic field, and you know what's happening when you increase the magnetic field in the mixed state of a superconductor. You're increasing proportionately the vortex density, so that at some point you're going to reach a magnetic field, and that turns out to be just in the region of this turnover, in which the spacing between the vortices marks the vortex core electric current reversal or supercurrent reversal from being counterclockwise in the core to clockwise outside the core in this calculation of Sols and Escherich. So it's on the scale of this unusual structure of supercurrents which can be explored and gives rise to the manifestation of broken time reversal symmetry that we claim is manifest here. Now, Jim showed this graph before in his talk last week, which is for different samples of different zero temperature resistivity resistivities, you get different TCs. But for a same crystal, for a crystal, say, which has this TC 550, then what you observe is an anisotropy in the resistivity, the zero temperature resistivity for that particular crystal, which you can easily measure. Now, essentially all of these crystals that are shown here are from, they're just needles cut from the same crystal. After it's been annealed, fabricated, it's the same crystal, but just different samples, which were then annealed at different temperatures. And the different temperatures has an effect on the zero temperature resistivity. You can vary it over a range of, well, more than a factor of 2. So what is the reason for that anisotropy in the resistivity? Well, you might say part of that has the origin in the Fermi velocity. So for those of you who are familiar with this notation A is the slope of the resistivity as a function of temperature, which goes like T squared. And so for different orientations of the current along the C-axis or in plane, you'll get a different ratio, and that's proportional to the ratio of the Fermi velocity. So if you form this product here and take the ratio to this product down here, then this will give you the intrinsic anisotropy of the scattering process itself, and that's about 30%. So we know that the scatterers are anisotropic. And here's what they are. The first observations from Hong and Seidman were using electron microscopy. And now keep in mind the z-axis is out of the page for all of these images. So you're looking in the basal plane, if you wish. And what you see are lines, and they're all at certain angles, and those angles are at 120 degrees to each other. And you see the same thing in the optical image that Elizabeth Shem took from the faceted crystal that we had sent her. And indeed, you can also see, for again z-axis presentation here, you can see a starfish or a six-fold pattern in small angle neutron scattering. That's the background of the small angle, and that comes from this these stacking faults, which have been identified in electron microscopy. So when I go back to this plot, these samples here are all taken from the same crystal with the same chemical impurities. It's the annealing which produces variations in the stacking fault density. Now, this may be the more contentious part of the uranium platinum 3 story, and that is the susceptibility or the night shift. So this, the susceptibility, spin susceptibility can be inferred in part from the night shift, from the spin part of the night shift. And here in the work from Tu et al. In 2 papers, in 96 and 98 PRL, the NMR measurements are plotted here, they're green here. And over here, they're red. I took this from our paper in 2012, but anyway, so maybe it could have been better. But in any case, the NMR measurements are clearly such that the susceptibility and the spin susceptibility, therefore, as well, is temperature independent. And that's the same for the in-plane magnetic field. And so the conclusion is that you have equal spin pairing in all directions. And that's from its temperature independence, similar to the helium-3. However, the theory, the E2U theory, has that when you invoke that polyillumin requires that the D vector be locked along the z-axis, what this means is that you should expect for the orientation H parallel to C, you'd expect that the susceptibility would be temperature dependent. And that is, it should decrease. Now that's not observed in the NMR, these green data. And Jim Sauls argued that, well, perhaps there's spin orbit interaction, which at the surface we might know would be relevant to making that not possible. So we did the neutron scattering, polarized neutron scattering to check that, and we get exactly the same results. Now the neutrons pass through the entire superconducting state, 30% transparency. So this is a very convincing result from the neutron scattering, I think, which confirms that the NMR night shift measurements are on the money. However, does this mean that E2U theory and its dependence on HC2 is suspect? And I say not so fast. And for those of you who are not NMR aficionados, I want to point out McLaughlin's beautiful review in solid state physics of night shifts. And the night shift ratio being the night shift in the superconducting state at lowest temperature to that of the normal state, which is proportional to the spin part, or at least the spin part of the night shift, is proportional to the spin part of the susceptibility compared to the normal part of the normal state part of the susceptibility. And in the limit of boundaries or anything that invokes spin orbit coupling in proportion to the energy gap compared to the spin orbit spin reversal time as expressed by Phil Anderson, will give him that strong spin orbit scattering limit of a number 1 - 2 times something which could be small. And if the spin orbit time reversal scattering is large enough, then you'll just get the same thing. And what could possibly give such spin orbit scattering? It's clearly not the boundaries. That's not going to do the job. But how about the prism plane stacking faults? And so my proposal here is that the spin orbit and transport mean free path ratio is much less than 1 for spin orbit and transport. Now the specific heat, I know I'm getting on in time here. The specific heat for 3 of the crystals that we've grown has a phase window, I call it, the difference between the onset of superconductivity and the A to B transition, which changes depending on triple R in a systematic way. And if you look at that globally, for all the data that we've been able to take out of the literature, you see there's a correlation between the A phase window and TC. So whatever affects TC, which we think of as being mostly but not entirely, but mostly the scattering from defects, nonetheless, there seems to be a correlation. So the symmetry breaking field, we argue, could have a strong component from whatever it is that produces this reduction in TC that we associate with prism plane stacking faults. So perhaps the prism plane stacking faults, in summary, are responsible for the symmetry breaking field, which may not be static antiferromagnetism. So now for the last thing I want to say in the last word or two is that, if you look at the E2U state and accept that it's potentially still valid because of spin orbit scattering and time reverse scattering from prism plane scattering to account for the temperature independence and directional independence of the susceptibility. If you look at the A phase, it is more anisotropic. You can look at the nodal structure, equatorial and longitudinal nodes, whereas the B phase is clearly more isotropic. So therefore, you might expect from the theory that is valid and demonstrated for aerogel impurities in helium-3, the theory of Tuneberry et al., that's slide 25 if you're counting, that anisotropic scattering favors anisotropic triplet states. And so the A phase, therefore, which is more anisotropic than the B phase, anisotropic scattering should favor the A phase. So as you reduce the prism plane stacking faults, then you should favor the B phase. Even though it's the chiral phase, it should be favored. And that's what's observed. And so to summarize, finally, we have these, again, multiple phases and phase diagrams for helium-3 and uranium-platinum-3. They have certain similarities. The A phase here is mainly stabilized by strong coupling, and the A phase down here is stabilized by anisotropic scattering. And with that, I summarize here.
Yeah, thank you very much, Bill. It's a fantastic, absolutely fantastic talk. Yeah, I actually understand that. Yeah, much more than I had previously. Then, yeah, okay. So let me. I have a couple of questions. Let me first, to take the advantage of asking you. So for the A phase, first of all, on the pure helium case, what is the sound velocity of transverse sound velocity you measured for pure helium?
I'm sorry, what was the question, Pencheng?
What is the sound velocity?
Oh, what is the velocity itself?
Yeah.
Okay, that depends on how close you are to the square root of 12/5 order parameter mode. So it diverges. The sound velocity actually diverges as you approach that mode. And it goes to a relatively small value, much closer to the Fermi velocity when you go to the gap itself. So it covers a wide range. The velocity covers a wide range. That's an interesting problem I didn't have time to talk about, but yes, mostly this is understood. Theoretically, this is understood. The velocity is understood. It agrees well with the theory, but the attenuation of the transverse sound does not.
I see. I see.
And,
Let me quickly ask you one more question, because there's so many people wanting to ask you a question. So the other thing is, what's the role of spin-orbit coupling then in UPT3? I mean, you said that it's the impurity phase that give rise to the suppression or promotion of the A phase. So what is the role of spin-orbit coupling then in UPT3?
So my conjecture is you have these stacking faults that you remove a plane, right? So you definitely have a defect in the crystal, and so if you have a large spin orbit coupling, then for scattering from a defect like that can produce time reverse scattering, which then favors a stronger susceptibility. Okay. That's in the theory of all three of the Farrell and Anderson and Abrikosov and Gorkov have the same result.
Okay, thank you. Yeah, Taran?
Thank you. Yeah, so I have a couple questions. Yeah, first of all, very nice talk. It's very useful.
Very educational.
Sorry, there's a noise from outside. So the one question I had was, you did not mention anything about so in the helium 3b phase is a topological superconductor which is supposed to have a Majorana cone at the at the boundary. So what is the current status of seeing it or some experimental verification of that? I've seen some acoustic measurements in the past.
Yes,
I wasn't sure whether
That's correct. That may be the most direct manifestation of the Majorana cone from now transverse acoustic impedance experiments done at the Tokyo Institute of Technology.
There have been no other kind of other than that. That's all so far?
Well, I would say somewhat more indirect. I mean, the heat capacity measurements definitely tell you that there is a heat capacity residual that depends on temperature and the low temperature limit. So you wouldn't expect that unless there's bound states, Andreev bound states at the surface, and the Andreev bound states at the surface are effectively those are Majorana states.
Right.
Could I
one more question?
I add something to that?
Oh, sure.
So, Bill, there's also this beautiful experiment on electron mobility of electron bubbles at various depths below the B phase surface.
Ah, yes.
So when you combine that with a theory of scattering of quasi-particles and these Majorana states near the surface with the depth dependence, it fits beautifully the existence of the Majorana cone.
Oh, yes. Thank you for
which paper is that actually? Which reference?
Yeah, I'll put it in the chat, Tarun.
Sure. Thank you. I had one more question. Can I ask? Or
yeah, please.
So in the so when you have this aerogel, I mean the helium 3 in aerogel, let's say. So in the helium 3A phase, does the disorder induced by aerogel gives a finite density of state at the node? For example, like in nodal D-wave superconductors, when you have disorder,
yes,
you can get a finite density of states. Is that the sort of specific heat? If I look at a specific heat in the aerogel, how does it look like for helium 3A?
Well, to answer your question, the calculations of the density of states in the presence of quench disorder show substantial, a very substantial concentration of density states in the so-called zero bias regime. And these are basically the Andreev states associated with the particles of the aerogel themselves. And yes, so the heat capacity is consistent. I claim is consistent with that.
I see.
Yeah, but you can't talk anymore about well-defined nodes in the energy density of states is function of energy anymore, because there's a plethora of bound states.
Right, I understand. But it's at least it's enhanced the specific heat.
Yeah,
but the symmetry of the order parameters are nonetheless very well defined.
I see.
both A and B phases in the presence of aerogels are gapless phases. Even the B phase is gapless.
Mm-hmm.
So-
Alu, you have a question?
Thank you.
Yes. I had a very nice talk. I didn't know all this, so I am really learning there. But one question I have is in the case of helium-3, you show that you can suppress one of the phases by the anisotropy that you induce. Did you study how this happens if you change the magnitude of the anisotropy?
Yes, of course. Yes, that's the anisotropy is imposed in a beautiful way. Let's take the other extreme of strain, which is obtained by stress. That's by compression of the aerogel is very compressible, and so consequently you can continuously compress, if you wish, to whatever extent you want, and that we've studied that to a considerable extent, and it's a variable which we have control over. And yes, so we know what happens to TC. We know what happens to the AB transition as a function of stress, and there's some interesting physics there.
Is
But
there
when
a
you-
sharp transition? Is there a sharp transition?
Yes, the transitions. That's because the mean free path is so long.
No, okay. You are speaking of the transitions themselves, but if you change progressively the stress,
Yeah.
do you see a sharp onset of the disappearance?
Well, that best, Henri, that best comes from the characterization of the anisotropy itself. So the way that's done, the way we do that is using optical birefringence, because you can shine light on this darn thing, and you can measure with fairly high precision how much anisotropy is there. And if you don't apply the stress, then, or in other words, you don't have strain, then it's absolutely, there's no birefringence. You can make it, I mean, you have to make good materials to start off with, and that's a learning curve, I have to say. But nonetheless, when you apply stress, you can progressively see, as you continuously apply stress, measure the development of the optical birefringence. And we haven't done the same thing quite so carefully with small angle X-ray scattering, but you all see the same thing, basically.
Oh, Jim, you have a question?
Thank you very much.
Jim? Oh, he's muted. Yeah. So I was curious.
Sorry, sorry, Pincheng. I had my hand up earlier when Tarun was asking a question, so I'm good.
Okay. Yeah. So I was curious. How do you actually control the homogeneity when you string the gel? You know, whatever this gel cell you have.
Yeah.
I mean, it's typically because if the material is very soft, right? If you push it, only the boundary, become pressed, right? The interior is going to be the same, right? How do you make sure it's homogeneous?
Well, you grow the aerogel in a cylindrical tube, glass tube, you see, and then you use a plunger which has the same symmetry exactly, and the Poisson ratio is non-zero, but you don't allow it's not free. Now, when you take a picture, now if you want to do, we do optical birefringence. When you do optical birefringence, you get an image of the entire thing.
And it's quite homogeneous.
And you can therefore see from the light intensity in the photograph that you take how uniform it is.
That's remarkable. I mean, it's such a soft material, right? You can press it. If you think about a spring, right? I mean, spring inside, yeah, it's difficult to make it. Yeah, very soft. Difficult to make it homogeneous. Yeah. Okay.
Jim, are you typing?
Oh, I'm sorry. Pardon me.
I've worked with Jim so long. I even know the rhythm of his typing.
That's embarrassing.
Okay. Any other question? I mean, particularly from students. Any question, Jim, maybe Bill will be happy to answer. Yeah, I mean, that's the problem. We typically, in all of the talks, right, students are typically quite silent. Yeah. Which is unfortunate. Yeah. Oh, they either completely understand. Oh, okay. So we do have some questions. Okay, so yeah, go ahead.
On a division, yes.
Yeah, Anna. Yeah.
Can I also ask a question? Okay, it was a great talk. Thank you very much. So I enjoyed it a lot. So you discussed the A phase and the B phase in uranium platinum 3. So there seemed to be a subtle difference because of this anisotropic quasi-particle scattering.
Yes.
So, but why is there also a C phase?
Well, there is a C phase in the natural. You mean what stabilizes the C phase?
Yes. So if you increase the magnetic field.
Yeah. So what I understand from Jim, and he'll speak for himself here, is that if you were to eliminate the, if you were to completely eliminate the symmetry breaking field, then you would have only one phase.
Which is B phase.
Yeah, and that would be the B phase. And so therefore, by implication, the C phase, what's responsible for the C phase is a combination of magnetic field and whatever the symmetry breaking field might be. Is that okay, Jim?
Yeah, so I looked at it. I mean, if you start from zero field, you have a symmetry breaking field that's preferring the A phase over the B phase. So something that's breaking the two-dimensional representation into two nearly degenerate one-dimensional representations. So you have two states there close by. Now, if you turn on a magnetic field, you have another symmetry breaking field, which is the Zeeman coupling to the orbital angular momentum of the Cooper pairs. So now you have a competition between symmetry breaking fields that scales with magnetic field. So so in this original symmetry breaking picture, then sufficiently high field, you can stabilize a different phase, which involves both orbital representations again, but is in general complex because you have vortices embedded in it.
I thought the C phase was a rotation of the A phase. So like the order parameters rotated by.
I think in general, you'll have both orbital components present, and you build a vortex lattice out of them. But on truth, there hasn't been enough theory on that B to C transition. I don't think it's properly understood.
Okay, it's not completely solved yet, I think.
No.
Okay, thank you.
Okay, great. Yeah, thank you very much, Bill. I mean, yeah, this is a very, very illuminating. Think about the stuff has been discovered for so long, right? The problem still not solved, just like Strontium-Leucinate 04. Yeah, appreciate this very much. Yeah, thank you.
Okay.
Yeah, thank you very much. Thank you all.
Thank you, Peng-Cheng.
Thank you.
Pinching, for Tarun, I put a reference in there for him just so he knows.
Okay, great. Yeah, he thanked you already, I think. Yeah.
Okay, ciao.
Yeah, thank you, everyone.
Thank
Nice
you, Bill. Thank you, Bill.
Thanks, Bill.